Hello friends, I welcome you in lecture number 34 on hypothesis testing. In this lecture, we are going to discuss about chi-square test of independence of attributes. In this chi-square test of independence, we will be discussing that how we can check whether two variables which are categorical variables are related or not, or we can test the independence between the two categorical variables using this chi-square test of independence. In previous lectures we have talked about chi-square test of goodness of fit, and in that test we have only one categorical variable, and in goodness of fit test we are testing the null hypothesis that given population is following certain type of probability distribution. So that is a different test in which we are not familiar about the distribution of population, and we are testing the null hypothesis that given population follows particular distribution. So whenever you will have goodness of fit test, in the question you will find only one categorical variable, and in chi-square test of independence you will have two categorical variables, say variable 1 and variable 2. You will be given the sample which is containing different categories for given two variables, variable 1 and variable 2, and you have to test the null hypothesis that these two variables are independent. Now the formula for test statistic is similar to the formula for test statistic of goodness of fit test, which we are familiar: sigma observed minus expected frequencies square divided by expected frequencies. So this formula is similar to the chi-square goodness of fit test. Now to understand this test of independence, we are starting with this example. We will understand the method simultaneously with this question. To determine whether there really is a relationship between an employee's performance in the company's training program and his or her ultimate success in the job, the company takes a sample of 400 cases from its very extensive files and obtains the results shown in the following table. So here we have two categorical variables. One variable is performance of employee in training program. Another variable is success in job of that employee according to company's rating. So in this variable, which is performance in training program, there are three categories: performance is below average, performance is average, performance is above average. And here in this variable, which is success in job, there are also three categories: success in job is poor, success is average, and very good success. And they have taken a sample of total 400 employees and they obtain these results. So we can call all these results as observed frequencies. We have the data which is observed from this sample. So this is observed data, or all these numbers are observed frequencies. We can say that there are 23 employees whose performance is below average and their success in job is there are 23 employees whose success in job is poor. Similarly, we can say that there are 49 employees whose performance in training program is average, and similarly there are 49 employees which are in this category, very good success. So in this way we can interpret all these results, and this is the total for first column. We can say that there are 60 employees whose performance is below average. Similarly, there are 188 employees whose performance is average. there are 152 employees out of 400 whose performance is above average. Similarly, these are the totals corresponding to all these categories. There are 112 employees having poor success rate. Similarly, there are 121 employees out of these 400 whose success is very good. This is the data which company has taken from its very extensive file. And here we have to test the null hypothesis that performance in training program and success in the job are independent. So you can see there are two categorical variables: performance of employee in training program and success of employee in job. So we have to decide, or we have to test whether there is some relationship between these two categorical variables or they are independent. So whenever you have this type of problem in which you have two categorical variables, you can check whether there is a relationship between those two variables or not using ChiSquare test of independence. You will be having this type of contingency table in which you have two categories: performance in training program and success in job. These are two variables, not categories. Performance in training program is one variable, success in job is another variable, and these are the three categories for performance in training program, and these are the three categories for success in job for that particular employee. So here we have 3 columns and 3 rows, or we have 3 categories for performance in training program, 3 categories for success in job. Now remember, for this test we are going to apply ChiSquare distribution. So we will require number of degrees of freedom. So number of degrees of freedom will be given by number of rows minus 1 into number of columns minus 1. Here we have 3 rows and 3 columns. So we have 3 minus 1 into 3 minus 1, that is 2 into 2, that is 4. We will consider degrees of freedom equal to number of rows minus 1 times columns minus 1, or we can say that number of categories minus 1 for both the variables. So number of rows will be equal to number of categories for this variable success in job, and number of columns will be equal to performance will be equal to number of categories for this variable performance in training program. Now we have to test the null hypothesis that these two variables are independent, and level of significance is given as 0.01. So first step is to write down null and alternative hypothesis. Null hypothesis is always that given two variables are independent. Whenever we are applying this ChiSquare test of independence, we will always consider null hypothesis as that given variables are independent. Here null hypothesis will be performance in the training program and success in the job are independent, and alternative hypothesis is negative statement of this null hypothesis. That means performance in the training program and success in the job are not independent. Level of significance is given as 0.01. Test statistic is same as in the test of goodness of fit. Observed minus expected frequencies whole square divided by expected frequencies. Now how to calculate expected frequencies? All these are observed frequencies. So suppose I am interested in the expected frequency corresponding to this cell. We can denote these rows by say R1, R2, R3, and these columns, these are the rows R1, R2, R3, and columns can be denoted by C1, C2, C3. Suppose we are using these notations C1, C2, C3 for columns, R1, R2, R3 for rows. So this is the observed frequency corresponding to first row and first column, that we can denote by O suffix 11. Similarly, this is O suffix first row second column. This is O suffix first row third column. Similarly, this is O21 second row first column, O22 second row second column, O23 second row third column. This is O31 third row first column, third row second column, third row third column. So we have 3 into 3, 9 observed frequencies, and now we are interested in the expected frequencies. Now what is null hypothesis? Null hypothesis is that both the variables are independent. So suppose I am interested in the expected frequency corresponding to this cell O11, then I will denote it by E11. E11 is the expected frequency corresponding to this O11. So to write down expected frequency corresponding to this, we will consider this row total. This O11 is in the first row, so first row total is 112, and it is in the first column, so first column total is 60. So we will take product of this row total for first row and row total for this first column divided by total number of observations in the sample, which is 400. So in this way we can find out this frequency. Let me calculate this. If I find out 112 times 60 equal to divided by 400, then my expected frequency corresponding to O11 is 16.80. Again I repeat, suppose I am interested in writing the expected frequency corresponding to this cell, which we have denoted by O11, then because it is in the first row, I will consider first row total. Because it is in the first column, I will consider first column total. I will multiply these two totals and divide by total number of observations, which is 400. Similarly, suppose I am interested in the expected frequency corresponding to this cell, that we will denote by E12. Then this is in the first row, so I will consider 112, but now it is in this second column, so I will consider column total as 188. So instead of 60, here I will write 188. This 400 will be there in the denominator always. E12 means row total corresponding to first row times column total corresponding to second column, their product divided by 400, and it turns out to be 52.64. So in this way we have to calculate corresponding expected frequencies for each cell, because we will require to calculate value of test statistic, and it is sigma observed minus expected frequency whole square divided by expected frequency. So because this requires expected frequencies, we have to calculate expected frequencies for each cell. So here there are total 9 observed frequencies, so we have to calculate 9 expected frequencies, and I have calculated all those expected frequencies using this formula, row total into column total divided by total number of observations. So if I am interested in the expected frequency corresponding to this observed frequency, say Oij, then this expected frequency will be equal to ith row total times jth column total divided by sample size. This will be the formula for calculating expected frequency corresponding to this observed frequency, which is in ith row and jth column. Because this is in ith row, we are considering row total corresponding to ith row. Because it is in jth column, we are considering jth column total and dividing by sample size. Remember this formula, and in this way I have calculated all the expected frequencies. After you calculate expected frequencies, you have to check that all the expected frequencies are greater than or equal to 5. Here also it is required. Once you calculate expected frequencies, then you have to calculate value of test statistic. After calculating value of test statistic, you have to find out critical value for chi-square at given level of significance and given degrees of freedom. And remember, here also we will always have right-tailed test as in the case of goodness of fit test. So we will reject the null hypothesis if calculated value of test statistic is greater than chi-square critical value at given level of significance and given degrees of freedom. Number of degrees of freedom will be equal to number of rows minus 1 times number of columns minus 1. So this is all about this chi-square test of independence. I have written all the necessary details for writing the solution of this example. Here you can see I start with null hypothesis. We have two variables, performance in training program and success in job. Null hypothesis is always that given two categorical variables are independent. Here two variables are performance in training program and success in job, and they are independent. We assume that null hypothesis is correct. Alternative hypothesis is negative statement of this. So here performance and success are independent. Here we write that performance in training program and success in job are not independent, or you can say that they are dependent. Level of significance is given as 0.01, and then I have calculated expected frequencies as I discussed. All these are expected frequencies, and this total must be equal to totals corresponding to observed frequencies. Here totals are 112, 167, 112, 167 and 121. So whenever you calculate expected frequencies, you should check that these totals must be same for this observed as well as expected frequencies. Here 60, 188, 152, 60, 188, 152. So once you calculate expected frequencies, you can check whether all these totals which you obtain corresponding to expected frequencies must match with totals corresponding to observed frequencies. So that will be a cross check for your calculations of expected frequencies. I have calculated all these expected frequencies using that formula, row total times column total divided by total number of observations in the given sample, and we can see all the expected frequencies are greater than 5 here. Next step is calculate value of test statistic. Test statistic is chi-square equal to sigma O minus E square divided by E. So I have to write down 9 terms here because there are 9 expected and 9 observed frequencies in our table. So I have to take care that I take difference between corresponding expected frequencies. Here O11 is 23, so I will consider E11. Here E11 is 16.80. So I have to write O11 minus E11 whole square divided by 16.80. Similarly, here I have O12 is 60. So I will concentrate on E12. This is E12. 60 minus 52.64 whole square divided by 52.64. Similarly, I have taken difference between O13 and E13. O13 is 29 and E13 is 42.56. So square of them and division. And in similar manner, I have written all these terms. The number of terms must be equal to total number of expected or observed frequencies. Here there are 3 into 3, total 9 cells. So total number of terms in this sigma must be equal to 9 because there are 9 cells. And after calculating all these things, I obtain calculated value of test statistic as 20.1788. Now next step is to decide critical value. So for that we will require chi-square distribution table. Before that we have to write down number of degrees of freedom. Here there are 3 rows and 3 columns. So 3 minus 1 into 3 minus 1, that is 2 into 2, which is 4. Level of significance given is 0.01. So I have to use chi-square table for alpha equal to 0.01 and degrees of freedom as 4. So let's go for chi-square table. Area to the right of critical value, these are the values of alpha. We are in search of alpha equal to 0.01, and these are the degrees of freedom. We are in search of 4 degrees of freedom. So we have to take intersection of this row corresponding to 4 degrees of freedom and this column corresponding to 0.01 level of significance. And if we take their intersection, we obtain this chi-square critical value. So let me remove these two, and I find that critical value is 13.277. 13.277. This is chi-square critical value, and I have written all these things here. Degrees of freedom are 4. This is 13.277, and this test statistic value is 20.1788, and it is obviously greater than this critical value. That means we are in rejection region. Therefore, we reject the null hypothesis. And null hypothesis is that performance in training program in success in job are independent, but we are rejecting the null hypothesis. That means these two variables are not independent. And here I have not sketched the rejection region. It is not required, but just for understanding we can have this rough sketch of chi-square distribution. Suppose this is the graph of chi-square probability curve. This is 0, and suppose this value is chi-square critical value at 0.01 level of significance, 4 degrees of freedom, and this we obtain as 13.277. And because alpha is 0.01, this area is equal to 0.01, and the area to the right of this, or the region to the right of this line, is rejection region, and calculated value of test statistic is 20.1788. So it will be somewhere here, 20.1788. That means we are in rejection region. Therefore, we reject the null hypothesis, and that means performance in training program and success in job are not independent. So this is very easy test. We will be given two variables, variable 1 and variable 2, and we will be having data in the form of table. Here we will have number of rows equal to number of categories for this variable, and number of columns equal to number of categories for this variable, and we will be having observed frequencies here. So using the formula, we will calculate expected frequencies. Suppose I am interested in the expected frequency corresponding to this cell, then here I will consider first row total into first column total divided by total number of observations in the sample. So in general, suppose I have OIJ. This observed frequency is in ith row and jth column. Then corresponding expected frequency equal to ith row total into jth column total divided by total number of observations in the sample. Using this formula, we will calculate corresponding frequencies for each observed frequencies. After that, we will check whether all the expected frequencies are at least 5. If all are greater than or equal to 5, then we will find out value of test statistic, which is observed minus expected whole square divided by E. And then we will calculate number of degrees of freedom, which is equal to number of rows minus 1 times number of columns minus 1. And once we have degrees of freedom, we will find out chi-square critical value at given level of significance with these degrees of freedom. And if calculated value of test statistic is greater than this critical value, we will reject the null hypothesis. And if this is less than this, then we will not be able to reject the null hypothesis. So this is very easy test. It is known as chi-square test of independence of attributes or independence of variables. Using this test, we can decide whether there is any relationship between two variables or not, or we can check, or we can test the hypothesis that two variables are independent using given sample data, which is always in terms of observed frequencies. So this is all about this session. I hope you are able to understand this chi-square test of independence. Thanks for watching.